Hi, welcome back to my class in Spherical Trigonometry. Those of you who missed the first lesson in this course, you may search for my video Art Teaches Spherical Trigonometry. Lesson 1 is Spherical Triangle. For today, we will take up solution of right spherical triangle. As in plane triangle, in plane trigonometry, a right triangle having a right angle, one angle is fixed at 90 degrees. In spherical triangle, one angle is also fixed at 90 degrees and it is the right angle. And to solve a spherical triangle means to find all the parts that are not given, or to solve a spherical triangle is to find the parts that are unknown using the parts that are given. In solving a right spherical triangle, we need two tools for solving a right spherical triangle, and these are the complement angle theorem and Napier's rules. There are two Napier's rules, but we start with the complement angle theorem. The complement angle theorem states that the trigonometric function of an angle is equal to the cofunction of the complement of an angle. Again, the complement angle theorem states that the trigonometric function of an angle is equal to the cofunction of the complement of an angle. Now, what is meant by complement of an angle? Or when do we say two angles are complementary angles? We say two angles are complementary angles if their sum is 90 degrees, in contrast to supplementary angles whose sum is 180 degrees. But in the solution of right spherical triangle, it is the concept of complement angle that we will use, and the complement angle theorem. Suppose we consider an angle A. And we denote the complement of angle A by A prime. If these two angles, A and A prime, where A prime is the complement of A, if these two angles are complementary angles, then their sum, if you add these two angles, their sum is 90 degrees. Their sum is 90 degrees. And we say A and A prime are complementary angles. And from this equation, we can solve for the value of A prime, the complement of A. If angle A is given, transpose A to the right-hand side of the equation. So we take the opposite sign of positive A and it becomes minus A. And we get A prime equals 90 degrees minus A. Hence, to get the complement of an angle A, simply subtract the angle A from 90 degrees. And the complement of A is denoted by A prime. And you can check by adding A and its complement, denoted by A prime, the sum should be 90 degrees if A and A prime are complementary angles. Now we verify the complement angle theorem using sine. We take the sine of both sides of this equation. We have sine of A prime, the complement of A, equals sine of 90 degrees minus A. A prime is the complement of angle A. Angle A is given. To find the complement of angle A, we subtract A from 90 degrees. And we take the sine of both sides because we want to verify the complement angle theorem that says the trigonometric function of an angle is equal to the cofunction of the trigonometric function, the cofunction of the complement of this angle. We simplify the right-hand side using a trigonometric identity from plane trigonometry. The identity for the sine of the difference of two angles. The sine of the difference of two angles is equal to the sine of the first angle. The sine of 90 degrees multiplied by the cosine of the second angle minus the cosine of the first angle the first angle is 90 degrees minus the cosine of the first angle 90 degrees multiplied by sine of the second angle A. But the sine of 90 degrees is 1 multiplied by cosine of A, we get cosine of A. And cosine of 90 degrees is 0. Multiplied by sine A, we get 0. So we get cosine of A. This is sine of 90 is 1. Multiplied by cosine of A is cosine of A. Minus the second term is 0. Because cosine of 90 degrees is 0. Hence, we have shown that the cosine of A is equal to sine of A prime. And sine is the cofunction of cosine. Cosine is the cofunction of sine. A prime is the complement of A. And A is the complement of A prime. So we have verified the complement angle theorem using sine. The sine of an angle is equal to the cofunction of sine. Cofunction of sine is cosine. Cofunction of the complement of the angle. The complement of A prime is A. Because A and A prime are complementary angles, their sum is 90 degrees. Or you may start from cosine. The cosine of an angle is equal to the cofunction of sine. The cosine of an angle A is equal to the cofunction of cosine, which is sine. Sine of the complement of A. And the complement of A is A prime. There are three pairs of cofunctions. The sine and cosine functions are cofunctions. Sine is the cofunction of cosine. Cosine is the cofunction of sine. And cosecant or secant or secant and cosecant are cofunctions. Secant is the cofunction of cosecant, and cosecant is the cofunction of secant. And the third and last pair of cofunctions are the tangent function and cotangent. Cotangent function. Tangent is the cofunction of cotangent, and cotangent is the cofunction of tangent. And you may notice that in each of these pair of cofunctions, one function has a co as a prefix. So these are the three pairs of cofunctions, and we state again that the complement angle theorem says that the trigonometric function of an angle is equal to the cofunction of the complement of the angle. The cofunction of cosine is sine, and A prime is the complement of A. We take more examples for applying the complement angle theorem. In each of the following given, we write each trigonometric function of an angle as a trigonometric function of the cofunction of the given trigonometric function, cofunction of the complement of the given angle. Hence, by complement angle theorem, sine of B is equal to the cofunction of sine. The cofunction of sine is cosine. And the complement of B, we denote by B prime. This is by complement angle theorem, the trigonometric function of an angle is equal to the cofunction of the complement of the angle. The cofunction of sine is cosine. The complement of B is denoted by B prime. If we know exactly the angle B, its complement is obtained by subtracting angle B from 90 degrees. Example, the angle B is 60 degrees. The sine of 60 degrees is equal to the cofunction of sine, cosine. Cosine of the complement of 60 degrees. The complement of 60 is 40 degrees. Sorry, the complement of 60 is 30 degrees. You subtract 60 from 90 degrees. 90 minus 60 is 30 degrees. This is an specific example with the given angle. The sine of 60 is equal to the cofunction of sine, cosine. Cosine of the complement of 60 degrees. The complement of 60 degrees is 90 minus 60 equals 30 degrees. We apply the complement angles theorem to find an equivalent function of an angle for each of these trigonometric functions. The tangent of angle C is equal to, by complement angle theorem, is equal to the cofunction of tangent. Cofunction of tangent is cotangent. And the complement of angle C we denote by C prime. Again, by complement angle theorem, tangent of C is equal to cofunction of tangent, cotangent, cotangent of the complement of C. The complement of C is denoted by C prime. But C prime is actually equal to 90 degrees minus C. But we do not know the value of angle C. So we simply write the complement of C is C prime. Number 3, we write an equivalent trigonometric function. We write a trigonometric function equal to cosecant of A. The cofunction of cosecant is secant. By complement angle theorem, the cosecant of A equals the cofunction of cosecant, secant, and secant of the complement of A. The complement of A is denoted by A prime. Example 4. What trigonometric function is equal to cosine of C? By complement angle theorem, cosine of C equals the cofunction of cosine, which is sine, Sine of the complement of C. The complement of C is denoted by C prime. Again, by complement angle theorem, cosine of C equals function of cosine, sine, sine of the complement of C denoted by C prime. And lastly, cotangent of B is equal to the cofunction of cotangent, tangent, tangent of the complement of B. And we denote the complement of B by B prime. In using the complement angle theorem, you should only remember that the three pairs of cofunctions are number 1, sine and cosine. Sine is the cofunction of cosine, and cosine is the cofunction of sine. The second pair of cofunctions is cosecant and secant. Cosecant is the cofunction of secant, and secant is the cofunction of cosecant. And the third and last pair of cofunctions is tangent and cotangent. Cotangent is the cofunction of tangent, and tangent is the cofunction of cotangent. And you should also remember that the complement of an angle is obtained by subtracting the angle from 90 degrees. If the angle is unknown, say angle A, we simply write its complement as A prime. But A prime is actually 90 degrees minus A if the angle A is given. The second tool that we need for solving right spherical triangles is given by Napier's rules. There are two Napier's rules, and these rules will help us write the equation from which we can solve for the unknown part of a right spherical triangle. And in the first lesson, we said that a spherical triangle is a triangle on the surface of the sphere. It is a part on the surface of a sphere. That's why it's called a spherical triangle. And the spherical triangle is bounded by three arcs of three great circles, three intersecting great circles. And from last time, we also said that a great circle is the intersection of the sphere and the plane that passes through the sphere, through the center of the sphere. And the center of the great circle is the center of the sphere, and the radius of the great circle is also equal to the radius of the sphere. If a spherical triangle is a right spherical triangle, then one angle is fixed at 90 degree angle. Or if a spherical triangle is a right spherical triangle, then it has one right angle, which means that only 5 parts of the right spherical triangle may vary. Because we said last time that a spherical triangle has 6 parts, and all these 6 parts are measured in using angular measurements, unlike in plane trigonometry where only the 3 angles are measured in angular measurements, while the other 3 parts or the sides of the plane triangle are measured using linear measurement. In spherical triangle, all the 6 parts are measured as angles, and the 6 parts are divided into 3. The angles at each vertex of the spherical triangle are on the surface of the sphere. And the other 3 angles which are actually the three sides of the spherical triangle, are known as the central angle because their measures are given by the angles subtended by the arc to the center of the sphere. Consider this spherical triangle with vertices A, B, C. We place the right angle at C, at angle C. So angle C is fixed at 90 degrees because we take it as a right angle. And because C is fixed at 90 degrees, only 5 parts of this right spherical triangle may vary. Those 5 parts are this side is small a, opposite angle A, the angle at vertex B or angle B, the side C, the side opposite the right angle C, the angle A or the angle at vertex A, and the side denoted by small b, the side opposite angle B. This is a right spherical triangle. In writing the Napier's rule in translating the Napier's rule into an equation, we need a device to help us remember the Napier's rules. And we call this device a mnemonic device. And this mnemonic device consists of a circle divided into 5 parts. And it's divided into 5 parts because in a right spherical triangle, as I said earlier, has only 5 parts that may vary because one part is already fixed at 90 degrees, the right angle of a right spherical triangle. So we place the 5 parts that may vary in this circle. And you start with the side connected to the right angle C. You may start with a small a or a small b. I will start with a small a. You can write a small a in any of these 5 parts of the circle. I will write a small a here. And then to write the remaining 4 parts, you may go in counterclockwise direction or clockwise direction. If you go in counterclockwise direction, next to small a, you will write angle B. And next to angle B, you will write the small c, the side opposite the right angle. And next to small c, you will write angle A. And finally, next to angle A is small b, the side opposite angle B. If you go in clockwise direction, you would obtain the same. If you start from A and you write A in this part, and you go in clockwise direction, next to small a is small b. Notice that we skip angle C because we already know angle C. We know that angle C is a right angle because we chose C as the right angle fixed at 90 degrees. We only place the 5 parts of the right spherical triangle that may vary in the 5 parts in a circle divided into 5 parts. So again, if you start with A and you go in clockwise direction, next to small a is small b, angle capital A, side is small c, and angle B. But this is not yet the mnemonic device that we will actually use for writing the equations from Napier's rules. The parts that are connected to angle C, or the parts that form the right angle, are retained in the mnemonic device. These parts that form the right angle are side A and side B. In the mnemonic device, we retain them as is, A and B. Again, in the mnemonic device, you write the parts of the right spherical triangle that form the right angle. And in this example, the parts of this right spherical triangle that form the right angle C are side small a and side small b. The other parts, angle capital B, the side small c, and angle capital A, you write them in the mnemonic device as complement. Instead of just angle B, we write complement of B, which we denote by B prime. And instead of small c or side C, we write complement of C, small c, which we denote by small c prime. The small c is the side of a spherical triangle. It is the side opposite angle C. But this side of the spherical triangle is measured. The length of this side is small c is the length of this arc through the vertices A and C. And the length of this arc is given by the angle subtended by this arc AC to the center of the sphere. So the side small c is actually in angular measurement. So small c has a complement. If the side C is an angle, it has a complement. And we denote its complement by small c prime. And finally, instead of A, we write complement of A, we denote by A prime. And this is the mnemonic device that we will use to write the equation using the two Napier's rules. We take another example before we state the two Napier's rules. Actually, from this spherical triangle, you can go directly to this mnemonic device, and from this mnemonic device, you can write the equation from using the Napier's rules. Consider this spherical triangle through the vertices P, Q, and R. I will choose the right angle. I will place the right angle at Q. So one angle is fixed at 90 degrees and it is at the vertex Q, or angle Q is right angle and its measure is 90 degrees. Which means that this spherical triangle is a right spherical triangle and only 5 parts will vary because the one angle is fixed at 90 degrees. And the 5 parts that may vary are the side P, angle R, side small q, angle P, and side R, opposite angle R. And we place these parts, these 5 parts of the right spherical triangle that may vary into a circle divided into 5 equal parts. We start with the part that form the right angle Q. You may start with R or P. I will start with P. Again, you may write P in any of the 5 equal parts of this circle. I will write P here. And you write the other 4 remaining parts. Beginning for P, you may go in counterclockwise direction or clockwise direction. If you go in clockwise direction, next to P, you write R. We escape angle Q because angle Q is already known and it is a right angle. Its measure is 90 degrees. We only place the 5 parts of the right spherical triangle in this circle that may vary. That's why we escape angle Q, because it is given as 90 degrees. Hence, after P, if you go in clockwise direction, you write a small r. Side R. After the side R, you write angle P. And then side Q. Angle R. And we are back to P. If you go in counterclockwise direction, we started out with P. Next to P, you write angle R, side Q, angle P, and then side R. But again, this is not the mnemonic device for writing the equations using Napier's rules. We write the parts that form the right angle Q. In the spherical triangle, the parts that form the right angle are sides R and P. In the mnemonic device, we retain these two parts, R and P. We write them as is. P and R. And the other three remaining parts, we write them as complement of these three remaining parts or these three angles. In the mnemonic device, we write R as complement of R, denoted by R prime. And instead of Q, we write complement of Q, we denote by Q prime. And angle P, we take its complement and we write P prime. Capital P prime. This is the mnemonic device that we will use for writing, for translating the Napier's rules into equations from which we can solve for the unknown parts of the given right spherical triangle. But in writing the Napier's rules, in these 5 parts of the right spherical triangle, there are parts that have to be identified because they are mentioned specifically in the Napier's rules. These are the middle part, the adjacent parts, and the opposite parts. Again, in this mnemonic device, there are 5 parts. These are the 5 parts of the right spherical triangle that may vary, except that the 3 parts are written as the complement of the original angles. But among these 5 parts, one of them will be the middle part, 2 of them will be the opposite parts, and 2 of them will be the adjacent parts. The opposite parts and the adjacent parts are identified only once you decide which part should be the middle part. We take an example for identifying the opposite parts and adjacent parts. To do that, we take each of these 5 parts in the circle as a middle part. First, we take the small a as the middle part. If the middle part is small a, we identify the adjacent parts. There are 2 adjacent parts. The adjacent parts are small b and complement of b. They are adjacent parts because they are adjacent to A. they are next to A. These are the two parts next to A. Immediately next to A or adjacent to A. So the adjacent parts of small a are B, small b, and angle B prime or complement of B. Again, if we take small a as the middle part, the parts adjacent to small a are small b and complement of B because they are immediately next to the middle part A. And the two remaining parts will be the parts opposite small a. And we write opposite parts. The opposite parts now are complement of A and complement of side C. This is small letter C. If you take a different middle part, the adjacent parts and the opposite parts will change. Example, you take a small c prime or complement of C as the middle part. If you take the middle part as a small c prime, the parts that are immediately next to c prime are complement of A or A prime and complement of B or B prime. Thus, A prime and B prime are the adjacent parts, adjacent to the middle part, C prime. We write adjacent parts. The adjacent parts are angle A, complement of angle A, and complement of angle B. C prime is the middle part. These are the adjacent parts, and the two remaining parts, the sides small a and small b, are the opposite parts. The parts opposite the middle part C prime. We write opposite parts. Opposite parts now are the sides small a and small b. Another example, suppose we take complement of A as the middle part. We write middle part. The middle part is the complement of angle A. Angle A is one of the angles, one of the unknown angles in the right spherical triangle we had earlier. If A prime is the middle part, the adjacent parts are the parts that are immediately next to complement of A. This complement of A next to complement of A are side B and complement of small c. These are the adjacent parts B and small c prime. If A prime is the middle part, the adjacent parts are B and small c prime. And the two remaining parts are the opposite parts. The parts opposite A prime, which we have chosen as the middle part. We write opposite parts. Opposite parts are small a and B prime. So we have chosen A as the middle part. These are the adjacent parts and these are the opposite parts. If C prime is the middle part, adjacent parts are complement of A and complement of B. And opposite parts are side A and side B. When we choose A prime or complement of angle A as the middle part, side B and complement of C are the adjacent parts, and A, side A and this angle, complement of B are the opposite parts. The parts opposite angle A prime. If you choose B prime or complement of B as the middle part, the adjacent parts are side A and small c prime. And the opposite parts will be B, side B, and angle A prime. If you take small b or side B as the middle part, the adjacent parts are small a and angle A prime. And this will be the opposite parts, C prime, small c prime, and B prime, or complement of B. For your exercise, please try the following. Each of these is a right spherical triangle. In number 1, we have the spherical triangle with vertices A, B, C, and the right angle is fixed at vertex B. In number 2, we also have a right spherical triangle with vertices D, E, and F, and the right angle is fixed at vertex D. For each of these right spherical triangles, you draw the mnemonic device, a circle divided into 5 equal parts. And you will write the 5 parts of this right spherical triangle that will vary in this mnemonic device. You remember that you write the parts in the mnemonic device. You write the parts adjacent to the right angle, or the parts that form the right angle of the right spherical triangle as is. In number 1, the parts of this right spherical triangle that form the right angle B are A and small c. You write them as is, and the other 3 remaining parts, you write them in the mnemonic device as complement of the original parts or angles. And then, after you have drawn the mnemonic device, you consider each of these 5 parts as a middle part. And for each middle part, you identify the adjacent parts and the opposite parts. You do the same for the second right spherical triangle. For this right spherical triangle, construct the mnemonic device. You start with the parts of this right spherical triangle that form the right angle. And for this right spherical triangle, those are the parts side E and side F that form the right angle D, and you write them as is. And the other 3 parts, you write them in the mnemonic device as complement. Instead of F, you write F prime. Instead of D, you write D prime. Instead of angle E, you write capital E prime in the mnemonic device. And after you have drawn the mnemonic device, you take each part as a middle part. And for the middle part, you identify the adjacent parts and the opposite parts. Because in writing the equations using the 2 Napier's rules, you have to know which are the adjacent parts and which are the opposite parts. The adjacent and the opposite parts of the given middle part. Because the 2 Napier's rules specifically stated the middle part and the adjacent parts and the opposite parts. And we need to know which parts are the middle part, the adjacent parts, and the opposite parts in writing the equations using the 2 Napier's rules. And we will do that in lesson 3. If you have any question about the lesson today, you ask your question in the comments below. And don't forget to subscribe to my YouTube channel, Art Kalison. Thank you.